Hi, I'm Russell Fox, and today I'll be talking about the conceptual design review for the dryer efficiency profile improvement project for the University of North Carolina, Charlotte Distance Education Senior Design Project. My faculty member mentor is Dr. Scherer, and my project partner is Jason Bilk. Today we'll be talking about the project description, the requirements, the performance specifications, the timeline of the project, the design alternatives, the costs of the project, and in the end we'll have a detailed description of the project. To give you a little bit of background, my partner Jason Belk works in a family business that repairs and also troubleshoots home appliances. My background is in test system design and automation, and also circuit design. The two of us together thought that we could come up with an attachment that you place on a dryer that improves the efficiency of the dryer. That project will consist of 3 parts. The first part is the test set. The dryer test set will monitor 3 variables of the exhaust of the dryer and also monitor current that the dryer consumes. The testing will consist of a dryer that we select and finding a standard of close to run tests on. The third portion of the project is to design an energy efficient dryer control, and from now on I'll be referring to that as a dryer attachment. And the dryer attachment will improve the efficiency of the dryer by simply turning it off when the clothes are dry. Here we have our requirements. There's 6 of them. The first requirement is to design a dryer test set. Design a robust test set that monitors the parametric data of the exhaust and also the current consumed by the dryer. The 3 sensors in the exhaust will consist of a relative humidity sensor, a temperature sensor, and also an airflow sensor. The second requirement is perform testing. To perform testing, we first have to find a sample, which would be a dryer, and control, which would be clothing, and then we'll just run various tests on the clothing. An example would be running clothing made of different materials at different saturations, and we can measure the saturation by weighing the clothes to see how much they weigh, to see what the moisture content of the clothes are. The third requirement is to analyze the test data. We'll review the sensor parametric data to establish limits for the attachment and the attachment control. So design an energy efficient dryer control, and that is the attachment that I just mentioned. And we'll design a prototype, and once we design the prototype, it'll take us to the 5th requirement, which is to test the prototype. And we'll run tests on the prototype and compare it to the parametric data that we acquired from the test set and see how the 2 line up. The 6th requirement is to document the entire process. We must adhere to the University of North Carolina, Charlotte documentation protocol. We have here our performance specifications. There's 4 of them. P1 is to design an accurate dryer test set. P1 will be measured by completing the calibration process on the sensors in the test set, and the process will involve calibrating to a standard piece of equipment within the range that the operating range that the test set will be run at. So for example, the current will be run from 0 to a maximum of 30 amps of a dryer. So we calibrated the current by taking a current transformer and an ammeter and running through a range from 0 to 30 at 5 amp increments, and saw if there was a linear correlation between the known ammeter and then also the current transformer used in the test set, and then just simply interpolated the ammeter data and made a best fit for the current transformer that's in the test set. So P2 is an energy efficient dryer control must create an energy savings. That can be measured by simply comparing the power consumption of a dryer prior to installing the attachment and then afterwards, and seeing what the difference of the power consumption is of the clothing dryer. P3 is improvement costs cannot exceed money saved over the lifetime of the dryer. So that can be measured by performing a cost analysis on the attachment, and it will consist of an opportunity cost of using the attachment as opposed to not using the attachment over the life of the dryer. And the two main benefits will be saving on repairs of your dryer, because it'll run less. The attachment will cut the dryer off and won't run as long. And the second will be a cost savings on your power bill. So those are the two main benefits that the attachment will provide. On P4, energy efficient dryer control does not interfere with the dryer operation. This will be measured by ensuring that the attachment installed does not affect the operation of any dryer. That's universal. So the attachment will be in the exhaust of the dryer with your sensors, and then your dryer will have a plug that plugs in to a plug that has a relay on it that plugs into the wall. So your dryer attachment that's on your exhaust will monitor the relative humidity, temperature, airflow, and when it reaches a level that says that the clothes are dry, it'll turn off the relay that's allowing power to go to your dryer. So basically, the attachment should work on any dryer and not affect the operation, because it's not an intrusive attachment. Here we have a timeline of the project. It's broken down into various items of test system hardware design, test software design, test the system construction, test system debugging, test system calibration, test system documentation and presentation. Then we have the second phase of the project, which is testing, testing documentation and presentation. After that, we go into the third portion of the project, which is prototype design and prototype testing and prototype documentation and presentation. This is broken into an x-axis of days that account all the time until the end of the second session of the upcoming summer session. Design alternatives. There's two design alternatives, or two parts to the design alternatives. The first part will be dryer test set. We could have used another platform like Visual Basic or C# or any other automation software to acquire the data. We use LabVIEW because we were comfortable with that tool set, and it just makes sense to use something that we were more comfortable using. We could have selected different sensors for current, relative humidity, temperature, and airflow. The reason that we selected the sensors that we did is a confidence level in those manufacturers. For instance, Omega was the relative humidity and temperature sensor probe in one that we decided to go with, and Omega makes excellent temperature sensor probes and also relative humidity probes. I've had experience with using their products in the past in test systems that I've designed before. Energy efficient dryer control. A design alternative could be sensor placement. Instead of having the attachment go in the exhaust of the dryer, it could, maybe the sensors could be placed into a dryer filter, or excuse me, lint trap, and acquire the parametric data there as opposed to in the exhaust. That's one alternative. Here we have the cost of all of our sensors. We included the cost of LabVIEW. Well, actually we didn't. We said it's free. USB 6008 was $169. The Omega temperature probe, $75. Got that on eBay. Discount there. The Kerwin airflow sensor was $50. The current transformer was free. Got that at work. Switch mode power supply was $18. Wires, various Radio Shack items, and resistors. Here the total is $327.22. So now we'll talk about a general description of the dryer test set. It'll measure 4 sensors. Again, that's current, relative humidity, temperature, and airflow. The dryer test set hardware description. It consists of a personal computer, National Instruments DAT card, Omega temperature relative humidity probe, Kerwin airflow sensor, 24-volt DC power supply, a Amron current transformer, and shunt resistors. Here we have a schematic of the dryer test set hardware, and you'll notice a 24-volt DC supply supplies your relative humidity and temperature probe. That's all in one again. And the airflow probe is also supplied by your 24-volt DC. And here you have your current transformer. So your current transformer steps down your current and provides a voltage drop across a 5-ohm power resistor, which goes into channel 3 of your data acquisitions card. So this current provides a voltage drop across this resistor that is measured by your DAT card. The airflow probe is a straight voltage from 0 to 10 volts that goes into your AI2 channel of your data acquisitions card. Your this Omega probe here as a relative humidity and temperature. They produce a current from 0 to 20 milliamps full scale, and this is a 276 76 ohm shunt resistor that the current produces a voltage drop that is monitored by AI0 and AI1 respectively. Your data acquisitions card is connected to a USB to your computer. So that's how all the data gets into LabVIEW, is through your data acquisitions card. So the dryer test set software description, again it was designed using National Instruments LabVIEW. Here we have a front panel example. This is your sensors. You have on and off options where you can turn them on and off. This log time allows you to set how often you want to acquire data in seconds. You have controls here. You have a start button and a stop button. This start button, when you press it, you'll be prompted by the program to ask you where you want to save the file. The file will save however often you tell it to log and determine on your location. It also have a timestamp that'll let you know at what time the data was taken. The measurement graph right here consists of current, temperature, relative humidity, airflow. All these will be distinguished by a different color. Current will be in amps, temperature will be in degrees Celsius, Relative humidity is in percent relative humidity, and airflow is in meters per second. These are indicators that just give you a numeric value of what those sensors are. Here you have a start date and start time. This elapsed log time is a counter to let you know when the next data acquisition will be performed. Here's a block diagram of the dryer control. The dryer control has three components: a feedback loop, a controller, and a relay. So the controller monitors the sensors, which is your feedback loop, and controls your relay. So say relative humidity is the sensor that we find that is an indicator of when the clothes are dry. Then the controller will monitor your relative humidity till it reaches, say, I don't know, 20% relative humidity. When it reaches that, it opens your relay because your clothes are dry. And that is the end of the presentation. I'd like to thank all of you for your time, and if you have any questions, feel free to email me at rfox14@uncc.edu. Thank you. Bye.